Hi class, this is Mr. Morris, and we're continuing talking about deviations from the ideal gas law, which is unit 3.6 in the AP Chemistry curriculum. So let's get started. First of all, what causes non-ideal behavior? So in the assumptions we make about ideal gas laws, there are two statements, and we've talked about these two statements that really make a difference, that are not true for real gases, and they affect both pressure and volume. So let's talk about the volume problem first. Well, the kinetic theory assumes that for an ideal gas law, the volume taken up by the molecules themselves is entirely negligible compared to the volume of the container. Well, for a real gas, that assumption isn't true. So the molecules themselves do take up a proportion of the space in the container. The space in the container available for the particles to move around is less, so that the actual volume, the space in the container, the volume in the container available for particles to move around is actually less than the measured volume of the container. So this diagram below kind of illustrates that. You can see as it's spread out, these particles are just bouncing all over the place, and maybe it doesn't look like they take up any space, but if you crammed them all into one corner, we do have a slightly lower amount of volume that the particles could bounce around in than the entire volume of the container. And that actually does have an effect more than what the ideal gas law assumes. This problem does get worse the more the gas is compressed. So if it's more compressed, then it's going to be a bigger problem. If the pressure is low, the volume taken up by the actual molecules is insignificant. So the pressure is low, the volume taken up is insignificant. But as the gas gets more compressed, the proportion of the total volume that molecules themselves take up gets higher and higher. That kind of makes sense. If we cram those, if it's a smaller volume and you've got more molecules in there, they take up a greater percentage of the volume that's available. So this problem becomes a bigger deal. You can imagine compressing it so much that the molecules are actually touching each other, and at that point the volume available for them to move would be zero. Now let's talk about the pressure problem. So this one's a little bit different. Another key assumption of the kinetic molecular theory for ideal gases is that there are no intermolecular forces between the molecules. Well, that's not really true for any real gas. If there weren't any intermolecular forces, it would actually be impossible to condense it to a liquid. But even helium, with the weakest of all of the forces, of intermolecular forces, it can be turned into a liquid if the temperature is low enough. So we know that this is not a true statement. So what effect do the intermolecular forces? It's kind of hard to understand at first, because for a gas molecule in the middle of the gas, there is no net effect. So it will be attracted to some extent to all of the other molecules around it. But on average, those attractions will cancel each other out. You'll have attractions from behind a molecule tending to slow it down, and they'll be canceled out by attractions in front of it tending to speed it up, so it's just going to cancel out. That's shown on the diagram on the left below. But despite all the intermolecular forces it's experiencing, they're just going to continue to move. It's going to continue to move in the same direction. So like we're looking at this example on the left. That's different if the molecule's about to hit the container of a wall. Let's talk about why. Now, there are not any gas molecules anymore, so let's look at the example we're talking about. So we were talking about this one. And if it's just surrounded by gas molecules, those attractive forces cancel out and it just continues in the same direction it was going to go anyways. But what about this one that's about to hit the wall? Well, now there are not any gas molecules in front of it, and the net pull, the net attraction, is where those gas molecules are, which is behind it. The molecule will slow down. It's attracted to the things that are behind it, which cause it to slow down right before it hits the wall. It won't hit the wall as hard, and because of that, it reduces the pressure. So, this is a key point. The overall effect of this is to make the measured pressure less than what you would expect, less than it would be if it was ideal. And the reason is because the only difference is when a molecule is about to hit the wall, the net pull is backwards because there are no molecules in front of it. The net pull is backwards into the body of the gas, and the molecule slows down just before it hits the wall. And because of that, it hits it less hard, it exerts less pressure, and the overall effect is to make the measured pressure, the actual pressure, less than the ideal pressure or the expected pressure. Let's check out a little bit more. So the effect is most important, makes the biggest difference at low temperatures. And why? Because at lower temperatures, the molecules are moving more slowly on average. So any pull felt by the gas, it has relatively more effect on slow-moving particles than if it were a faster-moving particle. At high temperatures, where the molecules are moving a lot faster, any small pullback is hardly going to be noticeable. So we can say at high temperatures, the effect of intermolecular forces is negligible. There is one final effect concerning intermolecular forces that's a little more subtle. As pressure increases, the molecules are forced more closely together, and if they're closer, the intermolecular forces become more important. Remember, as particles get closer to one another, the attractive forces are more noticeable. They're more strong. So, increased pressure, the particles are closer, and if the particles are closer, then there's a little more attraction between them. The molecules which slow the one just about to hit the wall down will be closer to it, and that's going to cause a greater effect. But what types of gases behave the most like an ideal gas? So we talk about these deviations from ideal gas laws. Some of the AP questions will be asking you to compare two molecules and say, which one behaves more ideal or which one behaves less ideal? We need to be able to evaluate that. Which ones behave the most like an ideal gas? Well, it's going to be something with the smallest possible molecules and the lowest possible intermolecular forces. If we're talking about just a type of molecule that is the most ideal, it's as small as possible while having the lowest possible intermolecular forces. That molecule is helium. It's got the weakest LDF. When it says the lowest possible intermolecular forces, we mean the weakest LDF. That comes from having the fewest electrons, and there's no net dipole, so it's nonpolar. So yes, it's helium. Helium is the one that consists of a small atom, and the van der Waals dispersion forces are the only thing that we have. It's got the lowest dispersion forces because it only has 2 electrons. Like helium, a hydrogen molecule also only has 2 electrons, so the intermolecular forces are going to be small, but not as small, because in the hydrogen molecule you have 2 atoms that can distribute the electrons over. As molecules get larger, the LDF will increase, and you might get other intermolecular forces like dipole-dipole attractions, hydrogen bonding, and so on. So gases made of molecules such as these will be much less ideal. So the more intermolecular forces you get, the less ideal they are. That's why helium is the most ideal gas. And we've got some diagrams on this page. A couple examples. When the gas particles are large and their volume is significant, how is the measured pressure compared to the ideal pressure? So I just copied, because this is in your notes, I copied those images to try to make it a little more visual. When gas particles are large and their volume is significant, how is the measured pressure compared to the ideal pressure? Well, we have to think about what's really changing. The pressure observed is going to be greater than the pressure ideal. Now, why is that? Because the larger molecules mean that you've got less space, less volume, for gas particles to move around. And if you have a lower volume, it leads to more collisions with the walls of the container than were expected, and you have a higher observed pressure. When there's a significant intermolecular force acting between gas particles, how's that going to change the pressure compared to the ideal pressure? The pressure observed is going to be less than the ideal pressure. Now, why is that? If we have greater intermolecular forces, looking at our diagram here, if I have greater intermolecular forces, that's going to slow that particle down. Stronger intermolecular forces makes the collision to the wall less forceful, and that lowers the observed pressure. So observed pressure will be less than the ideal pressure. And at what temperature and pressure does a real gas behave most like an ideal gas? At what temperature and pressure does a real gas behave most like an ideal gas? Well, we're looking for a condition with the lowest pressure and the highest temperature. At low pressures, the volume of the container is sparsely populated by gas particles. So thinking about this idea here, if we have low pressure, those particles are spread out more, so the volume taken up by them is very small. In this condition, the particles are very far apart. The effect of intermolecular forces will be negligible too, and the volume taken up by the gas particles will be insignificant. So both of those factors are true at lower pressures. That's important. At high temperatures, so low pressure, high temperature. At a higher temperature, where the molecules are moving a lot faster, any small pull back into the body, so we're talking about the image on the right now, I'm sorry, on the left, any small attraction by the intermolecular forces by the other molecules in the gas is going to be negligible. Any small pullback of the particle is going to be not noticeable. In high temperature, the effect of intermolecular forces is negligible. And that's it for our introduction to deviations from ideal gas laws. I hope this was helpful. The next video is going to have some example problems.